In this video, we'll see the Goldreich-Levin algorithm, which will list decode the Hadamard code in sublinear time. This will solve the problem that we posed at the end of the previous video. Let's recall where we left off in the last video. We had recalled the definition of the Hadamard code, which was all vectors of evaluations of linear functions over f2 to the m, and our goal was to list decode it in sublinear time. That is, given query access to some function g from f2 to the m to f2, our goal was to find a list curly L in time polynomial in m, so that for any w, so that the distance between g and the encoding of w is small, less than or equal to 1/2 minus epsilon, w is going to be in our list L with probability at least 2/3. Notice that we're asking to do this in sublinear time. That's because the length of a code word of the Hadamard code is 2 to the m, and we're supposed to find this list in time polynomial in m. That means that we don't even have time to look at this entire received word when we're coming up with our list. Just a note, in the previous video I was trying to call this omega. That's because it's slightly more canonical for it to be an omega in the context of the Fourier transform. But now I'm going to switch to calling it w because we're not talking about Fourier transforms anymore. I'm going to draw it exactly the same. Okay, so how are we going to solve this problem? You might recall that in a previous video, we saw an algorithm for locally decoding the Hadamard code. So let's start there. Here's an algorithm that attempts to solve this problem using the local decoding algorithm for the Hadamard code that we saw in a previous video. Here's the algorithm. So we're given query access to this function g from f2 to the m to f2, and our goal is to find some w so that the distance between g and the encoding of w under the Hadamard code is at most p for some parameter p. For this first try, let's just say that p is strictly less than 1/4. Remember that on the previous slide, we wanted p to look something like 1/2 minus epsilon for a small epsilon, and so this isn't going to cut it. But let's just assume this for now. So assuming that p is less than 1/4, here's the algorithm. We're going to draw some vectors, beta 1 up through beta t in f2 to the m, uniformly at random. Here capital T is some parameter that we'll choose in a moment. Now, for each I between 1 and m, we're going to do the following. First, for every single t, we're going to compute some estimate of w sub I based on our random choice beta sub t. The way we're going to do that is according to this randomized algorithm that we saw before for locally decoding the Hadamard code. That is, w twiddle of I is supposed to be equal to w sub I, which is another way of saying the symbol in this encoding that is indexed by EI, the ith standard basis vector. We saw an algorithm to do that in a previous video. The algorithm is to make two queries. Let's query g at the point we want, EI, plus our random beta t, and then add that to the other query, which is just querying at this random beta t. So this is just the two-query local correction algorithm we saw in a previous video, and by the analysis in that previous video, we have that this estimate is equal to the ith symbol of this encoding, aka the inner product of w and the ith standard basis vector EI, which is also known as wi, with probability at least 1 minus 2 times p, where p is this p here. Now we see why we wanted p to be strictly less than 1/4. That means that this success probability is strictly greater than 1/2, aka it's non-trivial. The reason that we are repeating this experiment t times independently is that we want to boost this success probability. We know that it's a little bit bigger than 1/2, and we want to make it a lot bigger than 1/2. And we'll do that just by taking the majority vote of all of our different trials. More precisely, I claim that when we take the majority vote of a bunch of independent trials, each of which is successful with probability strictly greater than 1/2, then the probability that our majority vote is incorrect after capital T trials is big O of 1 over capital T using Chebyshev's inequality. Just as an aside, let's work that out. So we have that the probability that each trial is incorrect is less than or equal to 2p, which is strictly less than a half, for all t between 1 and capital T. These events are independent. Actually, all we need is pairwise independence. So by Chebyshev's inequality, we can write the following. The probability that the majority is wrong is the same as the probability that the sum of all of these random variables, that is, the random variables that are 1 if the tth trial is wrong, is greater than or equal to t over 2. Subtracting 2 times p times t from both sides, we get this event. Now we can use Chebyshev's inequality to say that this probability is less than or equal to the expectation of this thing squared divided by that thing squared. And using the fact that these events are pairwise independent, the expectation of the square of this is the same as the sum of the expectations of that. So altogether, this is at most t times the expectation of any particular summand squared divided by this thing squared, which, if we assume that the expectation of this is exactly 2p, if it's less than that, it only makes our lives easier, is equal to 2p times 1 minus 2p divided by t times 1/2 minus 2p squared. And this is big O of 1 over t, assuming that p strictly less than a quarter is some constant. So we're hiding the dependence on p in this big O notation here. So going back to this slide, that justifies why the probability that our estimate, which is just the majority vote of all of these trials, is not equal to wi, is big O of 1 over capital T using Chebyshev's inequality. Now what we're going to do is we're going to do this for all of the different i's, and then from those w twiddle i's, we'll assemble some estimate w twiddle, which is just the vector of those w twiddle i's. We can take a union bound over all m values of I to say that the probability that w twiddle is not equal to w is at most big O of m divided by t. In particular, if we choose t to be some big enough constant times m, this is going to be small. In particular, we can make it strictly less than a third if we like. Therefore, provided that p is strictly less than a quarter, for any w that is within p of g, that is, so that the encoding of w under the Hadamard code is within relative Hamming distance p of the received word g, this algorithm will return that w with probability at least 2/3. That's great. That's almost what we wanted. The problem here is that on the previous slide, in this goal, our value of p was supposed to be close to a half, 1/2 minus epsilon. Whereas here, we're stuck with p strictly less than a quarter. And this is why we're going to need to do list decoding. This algorithm here is going to return a unique w. That's because there's a unique w that's within a quarter of any received word g. However, if we want p to be as big as a half, there's not going to be a unique code word within radius p of w anymore. So we're going to have to adapt this local decoding algorithm to come up with a local list decoding algorithm. As a warm-up, here's an adaptation of the algorithm where we are assuming that we have access to a magic genie. In more detail, the algorithm goes like this. As before, we are given query access to some received word g, and we want to find w so that the encoding of w in the Hadamard code is within Hamming distance p, or relative Hamming distance p, of the received word g. Now, though, we're going to want p to be as large as a half. Since there might be multiple different w's that satisfy this, let's imagine we have access to a magic genie who has one such of those w's in mind. And now consider the following algorithm. We're going to do exactly the same thing as before, so draw our beta t's in f2 to the m at random. And then we are going to ask our genie for b1 up through bt, so these are just bits in f2, so that b little t is equal to the inner product of w and beta t. Yes, I know we don't have a magic genie, and if we did, we could just ask the genie to solve the problem, but just bear with me for a minute. So we're going to ask the genie for this specific piece of information for the particular vector w that the genie is thinking about. Then we're going to do exactly the same thing as before, except here, when we used to have g of beta t, we're now going to have what the genie told us, b sub t. And then the rest of the algorithm is exactly as before. So let's go through the same analysis that we did before. Suppose that w satisfies this, and the genie has this w in mind. Now I claim that this step succeeds with probability 1 minus p, whereas before it was 1 minus 2p. And the reason is that the probability that we fail in this step is now just equal to the probability that this thing is not equal to what we wanted it to be, which is the inner product between w and ei plus beta t. Indeed, if this is equal to that, and because the genie is always right, this is equal to that, then the sum of these two things, by linearity, and the fact that we're working over f2, is just equal to the inner product of w and ei, also known as wi. So now this failure probability is smaller. It's only p instead of 2p. That means that when we do our analysis here for the majority vote, we can replace 2p with p everywhere. And so instead of needing 2p strictly less than a half, aka p strictly less than a quarter, we're now okay as long as p is strictly less than a half. That is the probability that our estimate wi twiddle is not equal to the actual wi, is big O of 1 over capital T, as long as p is strictly less than a half. Then we can do our final step and union bound as before, and the probability that we fail is, as before, big O of m divided by t. And we can make this less than a third. So this is looking pretty good. This still runs in time polynomial in m, because we're going to choose t to be on the order of m, and then this is a for loop over m squared things total. And for any w, so that the encoding of w is within Hamming distance p of our received word g, we're going to return it with probability at least 2/3. And now p is allowed to be arbitrarily close to a half. However, the obvious problem with this algorithm is that we do not have access to a genie. However, this is where the connection to list decoding comes in. In our next try, we're going to just iterate over all possible genies, and that's going to give us a list of possible outputs. So here's the third try. We're going to exhaust over all possible genies and make a list. Here's our algorithm. Once again, we're given query access to our function g, and we want to find a list so that for any w, so that the encoding of w is within Hamming distance p of our received word g, w is going to appear in our list with probability at least 2/3. So here's our algorithm. As before, we'll draw beta 1 through beta t at random. And now we're going to initialize some list curly L to be equal to the empty set. And now we're going to exhaust over all possible genies. And what I mean by that is that we're going to iterate over all of the possible strings b1, b2, ... up to bt in f2 to the t that the genie from our second try might have outputted. Then we're just going to assume that the genie was going to say that and run the second try, that is the algorithm on the previous slide, with this genie in order to obtain some guess w twiddle. We'll add that w twiddle to our list curly L, and then we'll return it. Okay, so that's our algorithm. Let's analyze it. So first, let's pick some w so that this holds. We want to show that w is going to end up in our list curly L with probability at least 2/3. Now, there was some genie from the previous slide who would have answered consistently with respect to this w. So let's suppose that that genie is the one that answers b1, b2, ... up to bt. That is, there is some b1, b2, ... up to bt, so that a genie thinking of this particular w would say that. Then, when we get to that particular genie in this list, by the analysis that we did on the previous slide, as long as p is strictly less than a half, this algorithm is going to be correct with probability big O of m divided by capital T. So again, if we choose t to be on the order of m, we can make this greater than or equal to 2/3. Therefore, for any such w, with probability at least 2/3, it's going to end up in this list curly L that we return. And as before, we can take p all the way up to 1/2, or at least 1/2 minus epsilon. Okay, so this sounds great, but unfortunately, this algorithm also doesn't achieve our goal. Can you spot the problem? The problem is the running time. This algorithm no longer runs in time polynomial in M. In particular, the running time is going to be 2 to the big omega of M. The reason is that in order for this thing to be greater than or equal to 2/3, we needed to choose t to be on the order of m, but then in this for loop, we're exhausting over 2 to the t things, that's 2 to the order of m things. So we solved our problem, except this algorithm is prohibitively slow. In particular, we could just look at the entire code word g in that time. So this doesn't achieve the goal either. However, we're almost there. The solution to this problem is that we're going to use less randomness, so we don't need to exhaust over quite so many things. The key is that when we analyzed this algorithm, the second try, in particular the part with Chebyshev's inequality, all we actually needed was pairwise independence. We did not need full independence. So what we're going to do next is replace these capital T random vectors with significantly fewer random vectors and bootstrap those to come up with a much larger collection of pairwise independent vectors. Then we're only going to have to exhaust over the smaller collection of corresponding bits b. So let's see how this is going to work. Let's let little l be the log base 2 of capital T, where capital T is as in the algorithm we had on the previous slide. Now, for all L tuples of vectors beta 1 through beta L in F2 to the m, and for some subset A of the numbers 1 through L, we're going to define beta sub A to be the sum over all T in A of beta sub T. Similarly, for all sequences of bits B1 through BL in F2, and a set A, subset of the integers 1 through L, we're going to define little b sub A to be the sum over all T in A of B sub T. The reason we're doing this is that I claim that if these beta i's are uniformly random, then these random variables, the beta sub a's, are going to be pairwise independent. Notice that there are a lot more than L beta sub a's. In particular, there are 2 to the L beta sub a's. So this is allowing us to take log of t uniformly random vectors and come up with t pairwise independent vectors. Let's prove this claim real quick. So what it means to be pairwise independent is that if you look at any pair, say beta A and beta A prime for A not equal to A prime, then those two variables are independent. So let's fix A and A prime not equal to each other. We want to show that beta A and beta A prime are independent. But this is true because we can write beta A as equal to beta A prime plus the sum over all t in the symmetric difference between A and A prime of beta t. Because A is not equal to A prime, this symmetric difference is non-empty. That means that this sum is non-empty, and this sum is going to be a uniformly random variable that is independent of this one. That's because none of the beta t's that show up here have an index in A prime. But that means that no matter what beta A prime is, or in other words, conditioning on beta A prime, beta A is still going to be uniformly random. Therefore, beta A and beta A prime are independent. Okay, so now let's use this claim to improve our third try and come up with our fourth try. So here's our fourth try at an algorithm. It will be the last one. Now, instead of exhausting over all possible genies, we're going to exhaust over all de-randomized genies and make a list. The key is that there's going to be fewer de-randomized genies than there are original genies. I just noticed that I misspelled de-randomized. That's better. Okay, so here's the algorithm. As before, we're given access to some received word g that maps f2 to the m to f2. And for any w, so that the encoding of w is within relative Hamming distance p of g, we would like w to be in the list that we return with probability at least 2/3. As before, we're going to draw a bunch of random vectors beta I in f2 to the m. But now, instead of drawing capital T of them, we're only going to draw little l of them, where little l is the log base 2 of capital T. Now, as before, we're going to initialize a list curly L to 0, and now we're going to exhaust over all vectors b1 up through bl in f2 to the l. Notice that this is L here instead of T. Then we're going to assume that our sort of new de-randomized genie was going to say b1 up through bl, and we'll run our algorithm from the second try to obtain some w twiddle, but we'll use the genie that outputs the bits b sub a for all subsets a of the integers 1 through l. Notice that there are 2 to the little l, which is equal to t such bits ba, and so that type checks. This genie was supposed to return capital T bits, and here are capital T bits. Then we're going to add what we get, w twiddle, to our list curly L, and after we've exhausted over all possible genies, we're going to return curly L. Okay, so this is the algorithm. Let's analyze it. As before, let's fix some w so that this holds. Now, let's let b sub t be equal to the inner product of w and beta t for all t less than or equal to L. Notice that this implies that the inner product of w and beta a is equal to ba for all subsets a of the integers 1 through L. The reason is that we defined this beta a in a linear way depending on the beta t's, and this is a linear function. Therefore, when we're running this second try, using the genie with these BAs, that means that we might as well have been running this second try here, not on independent random vectors beta 1 up through beta capital T, but on these pairwise independent random vectors beta sub a. But as we remarked earlier, pairwise independence was all we needed for Chebyshev's inequality to work. Therefore, the exact same analysis goes through, and this step is correct with probability 1 minus big O of m over t. Therefore, by the analysis that we did before, the probability that this w twiddle is not equal to the w we had in mind for the iteration where the beta i's are like this is big O of m divided by t. Therefore, as before, we can take capital T to be on the order of m. That will imply that for any w, so that the encoding of w is within Hamming distance p of our received word g, w is going to appear in our list curly L with probability at least 2/3. And that's what we wanted. Okay, so now we know that this algorithm does what we want. How about the running time? Let's analyze that up here. So this algorithm, the second try, took time polynomial in m. And now we're going to exhaust over all vectors b1 up to bl in f2 to the l. This takes time 2 to the l, which is the same as 2 to the log t, which is the same as t. So the running time is poly m for the inside stuff times 2 to the l, which is equal to poly m times 2 to the log t, which is equal to poly m times t, which is all polynomial in m, since we chose t to be on the order of m. So that's great, that's what we wanted. Altogether, we've just proved the Goldreich-Levin theorem. So here's part of a slide we had before with the goal that we wanted. Given query access to some received word g, find a list curly L in time polynomial in m, so that for any w, so that the encoding of w is within relative Hamming distance 1/2 minus epsilon of g for some small epsilon greater than 0, the probability that w appears in our returned list curly L is at least 2/3. And what we've just seen, theorem, is that we can achieve this goal. Hooray! What we've just seen is a local list decoding algorithm for the Hadamard code. I haven't actually defined a local list decoding algorithm yet. I'll do that in the next video. For the moment, though, recall that the reason that we were interested in this goal in the first place from the previous video had to do with some application in learning Boolean functions. What does this say for that? We will come back to that also in the next video. See you there.